Okay, so I hope I'm audible. Uh, I'm actually having a bit cold, so I may not be able to speak as loudly and as like in a contiguous manner, or like I won't be able to speak continuously for a long time. So there might be some issues while me speaking, so I may stop for a while. So I may stop for a while in between. So I hope you understand. So that's all. So I guess we'll wait for 2 minutes, 2 more minutes, and let's see if no other people, students join, then we can start. So thank you. So I believe we can start, and let's see what other people join, so they can join in between, and then we can continue. But let's start for right now. So dimensional analysis. So it's actually one of the very important, what to say, tool in the subject of fluid mechanics. So I'm sorry I forgot to welcome. So okay. So welcome everyone. So welcome back again to the week 7 of the problem solving session for the introduction for the fluid mechanics and its for the course fluid mechanics and its applications. So in this week we will be dealing with dimension analysis. So as I was saying, dimension analysis is one of the most important, or very one of the most important tools in for us to have a better understanding of the concepts of fluid mechanics. So like after this, I guess we will eventually deal with boundary layer theory, as far I can guess, as per the course structure goes. But and in boundary layer theory we will boundary layer, if I may say, a boundary layer basically means that a small region, a very thin region in a flow field where the viscous stresses are considerable. Okay, so if this is this is a flat plate, and there is a flow over this flat plate. So let me not mention it like this. So let me say there is an incoming flow. I hope the screen is visible. So there is an incoming flow with u infinity. So this flow, when it strikes, it will form a boundary layer over this plate, flat plate. So there will be a boundary layer over the flat plate, and also there will be, okay. And this, what does the significant role that this boundary layer plays is that this efficiently divides this flow into two distinct parts, as I can say, like conceptually distinct, but in physical sense there's always some gradients that exist. But to make our to make the concepts a bit easy to understand, we can say this boundary layer efficiently divides this flow into two distinct layers or divisions, where the region within the boundary layer is a viscous region. The region above the boundary layer is a inviscid region, or more popularly potential flow region. So there may be some terms that may be quite new to you. For example, potential flow, that we'll eventually see when we dealing with boundary layer or potential flow theory. But it essentially means is that the concept of boundary layer that was developed by Ludwig Prandtl essentially tells us that the majority of the flow over a flat plate or any surface can essentially be studied by the concepts of potential flow theory, that it can be ideally assumed to be inviscid, since the Euler's equation or the potential flow theory equations will be good enough to predict the motion of fluid in those regions, in those inviscid or potential flow regions. I refer to these regions. But along with that, this flow would have a certain layer, a very thin region stuck to the surface of the object or the flat plate in this case, which would have significant viscous effects. So this region can be treated as highly viscous, and the viscous effects will be highly prominent in these regions. And since these two regions are physically different, because one region is viscous dominant and another region is inertia dominant, and viscous effects are not that dominant. So obviously the governing equation should also change, and we will eventually see how the understanding or the basic understanding of dimensional analysis helps us to derive the equations. There are the two different sets of equations. I should say equation set 2 and equation set 1. How we will see how a basic understanding of dimensional analysis helps us to derive these two different sets of equations derived from the same momentum equations that we have been dealing with right now. The momentum and the continuity equation, or basically the Navier-Stokes and the continuity equation, if we assume that the fluid is Newtonian, we will see how the basic idea of dimensional analysis helps us to derive these two different sets of equations from the Navier-Stokes and the continuity equation. Let me write it. Navier-Stokes and continuity equations. From that we can derive these two sets of equations that we will eventually see when we are dealing with boundary layer theory. But just to have an idea that having a basic understanding or basic knowledge of dimensional analysis will help us to derive these equations that would eventually help us to get some approximate solution solutions to the Navier-Stokes equations. Right. But till now we have dealt with exact solutions that we have taken some certain assumptions that, if considered to be true, would give us a steady nonlinear set of equations, nonlinear set of ordinary differential equations that is quite easier to solve compared to the original non-linear, original unsteady non-linear PD that was initially handed to us from the from the Navier-Stokes equation. So compared to that, the ODE that we get after the linear ODE that we get after implementing certain assumptions that, if held true, can help us to get a very simple ODE. So I would say PDE to ODE. So which is then quite easy to solve, and those solutions, that the flow over a flat plate, say, oh sorry, I'm really sorry, not flow over a flat plate, say flow between two parallel plates, or the co-ed flow, or the plane Poiseuille flow, that is basically the flow between two parallel plates, or the Hagen-Poiseuille flow, that is basically flow in a pipe, flow in a circular pipe. So these solutions are exact solutions because the governing equations are in closed form, are simple enough. Boundary conditions are simple, so we can get an analytical, closed form analytical solution of those equations. That's why they are the exact solutions. But here in the case of boundary layer theory, we make certain approximations to the scales that we use to derive these equations, and that's why these are considered to be approximate solutions and not an exact solution to the Navier-Stokes equation. But still, as I told you, engineering, or in the perspective of a fluid mechanics, a fluid mechanics researcher, having a fundamental idea of how a particular parameter changes in a flow field is good enough. It's good enough to get a proper understanding or proper conceptual understanding of whatever is happening in that particular kind of flow field. Like if we get an idea, if we get a rough idea of how a parameter may change within the flow field, if we get a rough idea by even simplifying the equations or even implementing some crude assumptions that may make a solution very inaccurate. Not that inaccurate that the solution is difficult to be acceptable, but inaccurate in a sense that the solution is acceptable, though it is inaccurate, but it gives us an idea of how a particular parameter or a variable, a flow variable, changes in that particular flow field, so that we can then model, we can make the we can get a particular the required idea of the flow field and make then certain models to solve our problems, right? So that's the very gist of any engineer or a fluid mechanics researcher. That is yes. So yes, that's what I wanted to tell. So yes. So I guess by now you understood why dimension analysis is so important. I don't consider it to be a separate chapter or addition to fluid mechanics, or a conceptual addition to fluid mechanics, but rather I understand it as a tool. Like for understanding physics, we need to know mathematics. Like mathematics is a tool. So similar to that, in the concept of fluid mechanics, dimension analysis should be considered as a tool rather than a concept, rather than new topic of teaching or learning. It should rather be taken as a tool that is usable, that can be used for any kind of fluid mechanics problem, or even other problems as well, that is not related to fluid mechanics but can also be related to other problems such as solid mechanics, or any other problems that are being governed by some certain set of governing equations. This is basically partial differential equations. So having an idea of dimension analysis is helpful in those cases also. So that's why it's very important to have a basic knowledge of dimension analysis. So I guess I've spoken enough to motivate you to learn about dimension analysis. So let's just go through it slowly. So so these are the basic definitions. So let me just dictate it. So if there's any doubt, you may stop and ask. So so in a simple words, like if you want to know what's dimension analysis, so it's basically getting an idea, getting a knowledge of which are the prominent scales which are the prominent scales that govern the flow field. I usually tend to speak something like Reynolds number is defined as rho, Vc, Lc and mu. Given that rho, if we are dealing with flow with constant flow properties, we deal with these two terms. Actually, the fundamental definition of Reynolds number comes with these two inherent terms, Vc and Lc, where Vc is characteristic velocity, and Lc is characteristic length scale. Okay. So these terms, characteristic velocity or characteristic length scale. So this term characteristic basically implies or tells us that what is the dominant velocity. Characteristic, like it will be characteristic basically means that which is the velocity component or which is the length scale, the dimensional length scale that characterizes the flow field, right? Gives the very identity to the flow field. So that's why it is called as characteristic, right? So, or in other words, you can say which is the dominant velocity component, that governs the flow field, or which is dominant length scale, right? Dominant length scale. Dominant length scale that governs the flow field. So in this case, if you see, I will just briefly discuss about boundary layer, because I guess this is the topic or concept in which the dimension analysis is extensively used. So without having a fundamental understanding of dimension analysis, you won't understand the very fundamentals or the very derivation of the equations for the boundary layers. So let me just briefly explain that. If there is flow over this flat plate, and so since there is a boundary layer, you will eventually see that this will have two velocity components. Okay, one along the x direction. So if I say denote it with u, and there will be a very small velocity component. Let me just zoom it a bit. So there will be a very small velocity component along the v direction. Along the y direction. Let me say there is v. It will be very small. Like it seems that they are comparable, but actually I should draw it a bit like this. So the velocity component along the v direction is much more larger than the velocity component along the y direction. You will eventually see how the scales, if we know the scales of various different variables in the flow field, how the understanding or knowledge of the scales that govern these various variables help us to get an idea of how the different other variables, such as having an idea of the scales for the coordinates or the length scales, having an idea of the order of magnitude of the length scales gives us a good assumption of how the order of magnitude of the velocity scales would vary in the flow field. So that's the beauty of dimension analysis. So from that we eventually discover that the velocity field along the y direction, this the v component, is quite smaller than the velocity component along the x direction. So dimension analysis helps us to get an idea, actually get a very proper idea with a good approximation. Then the velocity component along the y direction, x direction is much more larger than the velocity component along the y direction. So in this case, I would say the characteristic velocity of, like if it were should have been ideally the u component of velocity, but in reality it is u infinity that is chosen as the velocity component along the characteristic velocity for the flow or flat plate. Why? Because it's essentially because it is u infinity that drives the flow. That's again different concept that I guess we briefly discussed in coed flow. Like how the movement of the upper flat plate drives the flow. So u infinity or the inertia contained because in the form of the u infinity drives the flow. So that's why we take the characteristic velocity as a u infinity. But again, when we are now concerned with the characteristic length scale, so we'll again see that in the case of flow on flat plate, the characteristic length scale for determining the Reynolds number at the flat plate, in the different regions of the flat plate, the characteristic length scale is chosen to be the x coordinate system. But interestingly enough, what I must say, the significant changes in the flow physics or the dominant significant change in the flow physics actually takes place along the y direction. But then also, for determining Reynolds number in this case at least, we take the x coordinate as the characteristic length scale. So I guess there are a lot more things to be discussed before finally understanding the very crux of the boundary layer theory. But I guess you get a brief idea of how dimension analysis helps us to know what are the important or dominant flow parameters that actually govern the flow field, right? That actually drives the flow. There may be different flow parameters, but among them there may be certain parameters that will actually drive the flow. So dimension analysis helps us to get that idea. So I hope it is quite clear now what is dimension analysis, or why it is important. So I guess all the other content of today's discussion will be quite very simple to understand, because you know now the importance, so it's very easy for you to grasp the concepts now or the examples now. So that's fine. Sorry. So let me just dictate through the definition. So all physical events or systems that an engineer investigates are expressed in terms of physical quantities. That's basically the flow parameters or the flow variables. Okay. In case of fluid mechanics, a physical quantity is a property of a system or material that can be quantified by a measurement. So and these flow parameters or flow variables could be quantified. So there are various units of measurements that we know, that is mks, meter, kilo, second, cgas, centimeter, gram, second. These are various unit systems that we briefly we discuss or learn about in our class 11 according to the Indian education system. We learn about these different unit systems. We discussed about it thoroughly in class 11, so I just gave a brief reference. But still, like, I guess you need you know the different unit systems. So among them, since you know the unit system, so you know, following taking some particular unit system as our tool, or as our way for measuring, way for measurement, then considering that this taking a particular unit system, these flow parameters or flow variables can be quantified, right? Say if it is velocity, then it will be meter per second. If it is mass, then it will be kg, right? If it is force, then it will be Newton. So if it is pressure, it is Pascal. So these are the various units. So I guess it's very fundamental, so let's not dive deep. So again, this physical quantity that it is mentioned here, as I said, can be subdivided into the four categories: independent variables, independent parameters, dependent variables, and dependent parameters. So independent variables basically means the variables that are independent of the experiment or the flow measurement that we are taking or conducting, right? So in the case of any flow measuring experiment or flow field, even if it's not experiment, if you're doing some theoretical studies also, in those cases the independent variables are usually the coordinate system that we have chosen to define our, the coordinate system that we use chosen to define our system, right? So they, that is, so they this coordinate system that we choose are usually referred or taken to be as the independent variables in the this during flow measurement or any theoretical study that we conduct. Okay, so who is it? Let's see. So Prashant, just a brief, what to say, notice that I am not feeling that well today, so I may not be able to speak quite loudly, or I may even stop in between the session. So if at any point of the session you are not understanding anything, so you can just stop me and tell to repeat. Okay, so I hope you understand. So yeah, so getting an idea of the independent variables, now we have independent parameters. So in that independent parameters, we have the flow geometry, that's flow geometry, the angle of attack, the flow velocity, and the material properties. So these are the independent parameters that can exist. Say, and this was example was taken for flow over an airfoil. So let me just draw the airfoil. So these are the parameters that has been taken in the case of flow and airfoil. So I won't go into details. So just give you a visual understanding. So yeah. So these are taken as independent parameters because these parameters are well beyond what to say. These are the parameters actually that can be tweaked or usually changed while doing such experiments. Or specifically speaking, in the case of flow and airfoil, these are the parameters that can be changed. Like material properties are not usually in our hand, but if we are planning to choose a different fluid, then rho and nu, the kind of viscosity can be changed, right? Similarly, if you are planning to do experiment in a different atmosphere or different surroundings, say the different elevation, say, or you are planning to do experiment in a vacuum chamber or a pressurized chamber, then pressure can also be handled. But usually what we have in our hand is the geometry or shape of the airfoil that can be changed from our side, and that change in the geometry would help us to basically these parameters would act as an independent parameter that we will be able to tweak or change to get an idea of like how the change in these parameters would in turn result in change in other flow parameters, right? So that's why they are called independent parameters. So I guess it was clear. Then we have independent variables I've discussed. It is usually the coordinate system that we choose. Then we have dependent variables. For dependent variables, so in the case of dependent variables, we have pressure, U and V. So it may seem like they must be independent, but these pressure, velocity and the velocity components are actually dependent on the type of coordinate system that we choose, right? Not pressure because it's a scalar quantity, but especially the vector quantities, which is the velocity components, are very much dependent on the coordinate system that we choose. So that's why they come under dependent variables. Then finally we have independent parameters. So here, as it is mentioned here, it is total lift, total drag, total pitching moment. So these are again some modified parameters that are usually taken into consideration while any fluid flow experiment, and these are termed in the special case of flow and airfoil. So these are parameters that are being designed by the researchers so that it can help us to get a better physical idea of the flow field. It's not that without that we cannot get the conceptual understanding of flow and airfoil, but getting idea of these parameters, these dependent parameters, it is total lift, total drag, or total pitching moment. This is just one example. So this helps us in getting a very proper or clearer picture of what actually is happening in the case of flow and airfoil. And these are actually, you will see that these are actually one of very important parameters that govern the design of an airfoil. Like what is total lift, total drag, these are actually very important parameters that help in determining the design of an airfoil. So I guess that's clear. So then there are pi numbers. So these are also can also termed as non-dimensional numbers. Non-dimensional numbers. So in the case of fluid mechanics, you will see that we will be dealing with lots and lots of non-dimensional numbers. Not only in fluid mechanics, in other thermal sciences also, say heat transfer. I may be missing some important branches, but at least what I know from my knowledge, the concept of non-dimensional numbers are highly used or highly integral in the understanding core concepts of fluid mechanics and heat transfer. So we will be dealing it. There are lots of numbers. So actually, I also don't know many of them. We eventually get to know when we are dealing with a particular problem that has been modeled by that particular scientist, and that particular scientist name those non-dimensional numbers by their own names. So these Reynolds, Eulers, these are all some, and also someday it may happen that the future researchers may also name the non-dimensional numbers in terms in a way of honoring the original researchers who developed their own theories. So it may happen like that also, but okay, so that's not important. Just to give you an idea of how these numbers came into existence. Okay, so these three non-dimensional numbers or pi numbers are shown here because these three numbers are, as you will see, are actually an integral part of the fluid flow equation. I'm not saying that there cannot be other non-dimensional numbers that may be important in the case of fluid flow, but these equations are like coincidentally enough become an integral part of the non-dimensional flow of the Navier-Stokes equation. Okay, so let me just write it. See, I have written a star because right now, as an undergraduate or a very first year postgraduate students, this idea, this understanding that these numbers, like other than Reynolds numbers, say this Euler number and full number will eventually come into picture while non-dimensionalizing the Navier-Stokes equation, but it's actually not the case. If you focus a bit more, it's actually not the case. Sometimes different non-dimensional numbers can also come into picture by non-dimensionalizing the Navier-Stokes equation, given the fact that there may be different driving factors or driving forces that may drive the flow, right? And in that case, that driving factor or that driving factor would be indeed be taken into consideration while non-dimensionalizing the Navier-Stokes equation, and that will in turn lead to the emergence of different non-dimensional numbers, right? So that's why it's not a very hard and fast rule that these three numbers actually, but Reynolds number, it's quite integral. It usually comes into picture, but other than that, the Euler's number or the Froude's number, they may not come into picture given that how we non-dimensionalize our governing equation or what actually drives our flow, right? So let me just write it. Different non-dimensional numbers may come into picture depending upon what sorry again sorry, I'm really sorry. What drives the flow and how the equations are non-dimensionalized. Okay. So you will eventually see how this non-dimensional numbers comes into picture, but for now let's move ahead. So the concept of prototype and model. Okay, so I guess you know the difference between prototype and model if you have attended Professor Gupta's lecture, because there he has very beautifully discussed the difference and also with ample amount of examples. But just as a part of my own duty, let me just define these two. Okay, so if you say prototype, it's actually the life size or the approximately equal size of the actual model that we are going to study upon, right? If we are going to study upon flow and aircraft, a prototype would be a model that has almost similar dimension, or if not equal, right? So dimensions of the actual aircraft and the model that or the system that we have created to study, if the dimensions match quite a lot, like match means they're equal, then we can say that it's a prototype. But as we all know, it's not always feasible to do experiments on aircrafts on life size scaled prototypes. So it's not that easy. It's quite costly, and usually it's very difficult. Like say if you want to aircraft you may even create, but say if you are trying to understand the movement of microorganisms in a very highly viscous or in a Stokesian regime, so how is it possible to create a prototype that is of the size or scale of the that is having a length scale of the size of a microorganism? That's again a very challenging thing. So in order to so in order to tackle that problem, the engineers or the researchers came with the concept of a model. So a model essentially means that it's a scaled down or scaled up version of the actual system that we are going to study. Like if we are going to study an aircraft, we can scale down the model a bit. We can take a model that has a system that has a similar length scales but not exactly equal, right? So the dimensions of the length scales of the real system and the model may be similar but need not to be equal. And essentially they are not equal in most of the cases, and that's why the concept of model comes into picture, right? So now I hope you get the understanding of prototype and a model, and both of them are actually necessary in their own way. So I guess this is discussed in the lecture, so I will not go into deep into it. Okay, so then comes the concept of similarity. So while understanding the flow physics, as I mentioned, it's not always what I'm saying is not always, it's most of the time not possible to simulate the exact flow conditions, right? to replicate the exact flow condition or flow scenario while designing an experiment, right? It's not possible sometimes. It's maybe quite costly or maybe not feasible at all, because the length scales are far beyond the scope of possible manufacturing. It cannot be manufactured. So that's why it's usually what we do is we tend to create similar flow conditions or flow conditions that would aid us to understand the physics of the flow, obviously with some certain inaccuracies, but at least we will get to understand the physics of the flow, and that will help us to get the trend of variation of the flow parameters in that particular flow field. And I guess that's more than enough for us engineers and researchers to get an idea of how the flow physics actually works, right? So given that, we emphasize on creating similar flow conditions rather than exact flow conditions, right? And that's why the concept of similarity or the term similarity comes into picture. And in that case, while discussing similarity, we usually deal with geometric, kinematic and dynamic similarity. So the term itself implies geometric similarity implies similarity in the geometry, basically length scales or the dimensions or the length scale or dimensions of the model, right? Kinematic similarity means the similarity in motion, basically the different kinematic factors, that is such as the velocity or pressure, those should be similar. Like pressure, I guess, is difficult to handle, but velocity we can, right? So it can be that similarity is required, right? And we will see how that is achieved, right, by solving some problems. And then finally we have dynamic similarity. As the name itself suggests, a dynamic similarity usually means similarity in forces, right? So we will discuss a bit more about in a detailed manner in the later portion of the session, but I hope you get an idea. And more importantly, these three are not independent. Okay, these three are actually dependent, or I must say, I don't know whether I'm correct or not, successively dependent on each other. Right? Like in a manner, what I meant to say, what I mean to say is that a flow can achieve, if a model and a prototype, if I'm using the actual words, a model and a prototype can independently achieve geometric similarity. That's completely fine. But a prototype and a model cannot achieve kinematic similarity without achieving geometric similarity. So a kinematic similar model, like if it at all exists, like cannot be considered to be kinematic similar if they are not geometrically similar. Okay, that's the first thing. So kinematic similarity is dependent on geometric similarity, right? So geometric similarity must be satisfied in order to have kinematic similarity. Similarly, to have dynamic similarity, the flow should be geometrically and kinematically similar. So this cannot exist without the satisfaction of these two conditions, right? So these two conditions must be satisfied, or these are the precursors of satisfaction before arriving to the conclusion that the flow field is dynamically similar, or the prototype or the model are in dynamically similar conditions. So this is a very important concept that you need to know. So in order to have achieved dynamic similarity, the geometric as well as the kinematic similarity must be satisfied. So I hope it was clear. That's basically what this line basically concludes, summarizes what I wanted to speak. The physics of the problem should remain the same. Like once these three parameters or similarities are satisfied, basically means that the physics of the problem has remained the same between the prototype and the model. Okay, so that's why it's very, very important. Then checking the relevance of the non-dimensional parameter to the physics of the given problem. Yeah, that basically means is that we'll eventually see, as I mentioned, there are different pi numbers or non-dimensional numbers. So because given a flow field, this flow field can depend on n number of parameters, right? There can be different parameters, though there may be limited number of independent parameters, but from that you can create different numbers of dependent parameters and dependent variables. So these dependent variables and dependent parameters can indeed be very high in the case of a flow parameter, in case of a flow field, right? So to get a proper understanding of the flow field, it's very important for us to know which of these flow parameters or flow variables that would eventually constitute a non-dimensional number, and which of these non-dimensional numbers would actually play a vital role in governing the flow physics. So that's also very important, and you will eventually see that these important non-dimensional numbers are indeed found out by a very elegant theorem known as the Buckingham's pi theorem. So we will eventually discuss about a bit and also take an example. It's a very simple, elegant theorem that uses a very simple mathematical concept to help us to arrive into the non-dimensional numbers that actually govern the flow. So that's how important the Buckingham's pi theorem is. So we'll eventually see. Okay, so this basically trying to show how like once the non-dimensional parameters or non-dimensional numbers or the pi numbers that we eventually see it is told are known, the important thing is that for the flow physics to be similar, these non-dimensional numbers in the case of a prototype and in the case of a model should match. Okay, that's basically what I'm implying writing here. That the Reynolds number of the prototype and the Reynolds number of the model should match. Similarly, the Euler's number and the Ford number of the prototype and the model should match. But this matching does not happen arbitrarily, as you will see. We need to look like which flow parameter or physical force is actually driving or governing the flow. And once we know that, we can neglect the others and then compare these two forces or driving factors in the flow field and then finally arrive to a particular non-dimensional number that we need to match. Because these are not decided arbitrarily, okay? So these actually have a very crude, a very tedious manner. There exists a very tedious manner by which one arrives to a conclusion that yes, finally we need to match the Reynolds number of the prototype and the model so that we can finally calculate our required parameters. So how it happens, you will see there are various methods or approaches that the researchers have been using from the very inception of the concept of dimensional analysis. So they improved upon the theory and eventually finally arrived to the Buckingham pi theorem, which actually gives us a very elegant way to arrive into the non-dimensional numbers that need to be matched in the case of prototype and model, so that we can say that the flow physics is similar in the case of the prototype and the model. Okay, so I hope I was clear. That's why this matching is done here. So okay, so that basically what is mentioned here, that if these are similar, if this a flow field, and these all of the three are all three of them are important, then if this condition is satisfied, as it is mentioned here, under these conditions, then so it is mentioned here that under these conditions the non-dimensional governing equations and the normalized boundary conditions are identical, and the non-dimensional solutions of normalized variables will be identical. So basically it's actually vice versa. Like you will see that the first approach tells us that, like, from the governing equation itself we get an idea of what are the non-dimensional numbers that will come into picture. So we tend to equate those non-dimensional numbers and then compare these non-dimensional numbers by knowing that which among these numbers non-dimensional numbers or factors will actually govern the flow, and once we know that, the other forces or other factors can be neglected, and then we compare these two forces or factors or driving factors that drive the flow, and then finally get an conclusion, and then compare these two non-dimensional numbers. Okay, so am I audible? Okay, so uh, we actually joined a bit late, so we are continuing with the dimension analysis part of the fluid mechanics and application NS application course. So we will discuss the concepts and solve problems along the way. So if you have any doubt, you can please stop and ask. Okay. So just as I mentioned here, the two flows, that is model and the prototype, are similar flows if the values of the non-dimensional pi numbers formed with the uniquity parameters are identical in the two flows. Okay, this is basically what we were discussing previously, that if these two non-dimensional numbers are equal in the case of both the prototype and the model, then we can say that the flows are similar. Okay, and ideally, the lesser these non-dimensional numbers required to parameterize or to characterize the flow, better it is for us. Because it is much easier to model a problem with lesser number of variables rather than having more number of variables. So it is quite easier for us to handle lesser number of variables. So ideally, it is better if we could find ways to discard the non-dimensional number that can be discarded by disregarding the factors that do not actually play significant part in driving the flow, right? That is where the concept driving factor of a flow field comes to picture. So we will see. Okay, so let's just see a brief example of non-dimensionalizing different flow variables. Okay, so this example, I guess, was again taken in the lecture by Professor Gupta. So here we are dealing with a shear stress. Okay, shear stress in the case of a Newtonian fluid, right? So this, since the flow is Newtonian, it's basically proportional to the velocity gradients in the flow field. So I written here, it's one of the components, one of the 9 components of the shear stress tensor. No, I must not say shear stress, I must just say stress tensor. So here we may write tau is equal to mu dou u by dou y plus dou v by dou x. So let me just stop a bit. So I hope one of the students can help. So Snehal, am I audible? You may unmute yourself if you are available. Okay, so the thing is that we tend to make these sessions quite interactive so that it's helpful for you and helpful for the TAs as well. So let me request you one thing. So see, there is an expression on the screen that shows that tau is equal to mu dou u by dou y plus dou v by dou x. Okay, so since mu is an flow parameter, so ideally there cannot be any scaling done for that. So can you tell how can you scale the velocity components in this case? Like if you have attended the sessions, you will know how they are scaled. So can you tell how they are scaled, the velocity components? Given that you know nothing about the flow field right now, like which scale is dominant, you don't know. But in general, if you want to scale the velocity components and the length scales, how are you usually scaling it? Can you please tell? Okay, I feel that's fine. Okay, no issues. We will continue. So yes. So we see here that since we don't actually know how the, since it's a very it is randomly defined that this is a shear stress for Newtonian fluid, no, with no other specifications given to the concerned flow field or the flow geometry, so we don't we cannot actually predict how the scales of these different flow parameters will vary, right? So we just take an assumption that both the velocity components would scale as v naught, right, and both the Cartesian coordinates, that is the y and the x direction, would vary as L. Okay, so ideally v naught should be the, depending on the geometry, obviously depending on the geometry of the flow field, so ideally v naught is the largest velocity that the flow field can reach. That can be one scenario. Otherwise it's the average velocity that the flow field has, that the flow field achieves through its course of travel within the duct or the pipe. Okay, in the case of pipe flow, you can take the average velocity as the characteristic velocity as well, right? So that's why I'm mentioning how it can be different. But usually for most of the cases, v naught is actually the highest velocity or the largest magnitude of the velocity that the flow field can achieve. Okay. And here dou u star by dou y star, this star components usually is here at least are representing the non-dimensional components. Okay. So here we have so we can see after non-dimensionalizing we have mu v naught by L. This coefficient comes into picture, and to make some sense or to make some to arrive in a non-dimensional well-known non-dimensional number, we tweak with this expression a bit. Like we multiply or divide with certain constants in this case, and then we see that if we multiply and divide this factor with rho v, then we can see that a factor that is equal to 1 by Re comes into picture. So that's again helpful for us because we can directly deal with Reynolds number as a independent parameter rather than dealing with mu, rho, v naught and L separately, right? So all these four parameters can be reduced to a single non-dimensional parameter as an independent parameter that can be varied to understand the flow physics, right? So that's the usefulness of having non-dimensional numbers while while conducting fluid flow experiments or even doing some theoretical studies. So that's where the usefulness of non-dimensional number comes into picture. Okay. So similar to that, so now instead of a shear stress the shear stress terms themselves, we non-dimensionalize the entire Navier-Stokes equation, but in this case we deal with the steady form of the Navier-Stokes equation. This is basically the momentum equation for Newtonian fluid. So here you can clearly see that I can zoom it a bit. So here you can clearly see that the unsteady term is being neglected. So this is the vector representation of the Navier-Stokes equation. We again non-dimensionalize the equation by choosing certain scales to all the flow variables. So we see that by choosing certain scales, the Gorny equation very elegantly puts the reciprocal of Euler's number, Reynolds number and a Froude number as their coefficients to the non-dimensional form of the Navier-Stokes equation. Like you clearly see, the pressure gradient term has a 1 by Euler coefficient that is equal to 1 by Euler number. The viscous stress terms has a coefficient that is equal to 1 by Reynolds number, and the body force terms, given that this body force term scales as the gravitational force that acts in the flow field. Like if you take that assumption, this scales as the 1 by Froude number. This coefficient scales as 1 by Froude number. So this scaling that becomes quite handy, and like this particular scaling would tell us that the Euler's number The Reynolds number and the Froude number are the significant non-dimensional numbers that usually comes into picture while dealing with fluid flow problems. Fluid flow problems, like I'm sorry. So yes. So basically we have Reynolds number, Froude's number, and Euler's number. So this non-dimensionalization gives us an idea that these three non-dimensional numbers, pi numbers, play a significant role in dealing with fluid mechanics problems, and thus can be treated as the non-dimensional numbers to be compared between the prototype and the model, so that we could get the required values of the flow parameters in the case of a model or a prototype. Okay, so these are the numbers that need to be compared. This is the conclusion that we get by non-dimensionalizing the governing equations with some certain assumptions in our mind. That this is not actually always the case, but these are some general assumptions that we have taken, right? Because of which we get these numbers as the reciprocal of these well-known numbers, well-known non-dimensional numbers, at the coefficients of these different source terms in the Navier-Stokes equation. Okay, source terms and simply the three different terms, driving forces, driving factors in the case of the Navier-Stokes equation. Okay. Okay. Then again, in the lectures it is briefly discussed that in the case of Navier-Stokes equation, actually instead of explicitly pressure, it's actually the pressure gradient that comes into picture. So instead of scaling pressure, it would be ideal that we scale a non-dimensional parameter that would scale as a pressure gradient in the case of Navier-Stokes equation. Okay, so that was discussed a bit, so that's why I've written. So okay, again there's again a very important assumption that is being taken here. It's a very important simplification to the governing equation. Okay, so let me just read through it. The dependence of the non-dimensional governing equation on Froude number can be eliminated by defining a new variable capital P as P equal to P plus rho z minus P naught, right? So what it basically tells, as I told you, that the lesser non-dimensional numbers that we have to deal, the better it is for us to understand the concept of the fluid flow problem, right? So lesser the non-dimensional number, better it is. Simple words. Lesser the non-dimensional numbers to deal with, better it is for us, right? Because there will be lesser calculations that needed to be done. Okay. So just a few minutes. So that's why here they found a very good way to tackle with this Froude number, like incorporating this body force term in the pressure gradient term. That is usually a very common tactic or common method that is usually being applied while dealing with Navier-Stokes equation. So that's not quite new or something, but just it is shown here that how incorporating the Froude number along with the pressure gradient term helps in reducing a non-dimensional parameter in the case of the Navier-Stokes equation. Okay, so here we take, instead of P, we take capital P, where capital P is equal to P plus rho z minus P naught, where we will see that the pressure, if we take the derivative of this term, rho g term will come to picture, which is indeed the body force term, right? So yes, so I guess it is clear. So after doing the required simplification, we see that the equation has been simplified with these two numbers, so these two non-dimensional numbers as the coefficients. So okay, and it is told that the Froude number does not come into picture in the case of the Navier-Stokes equation. Only the Reynolds number and the Euler's number have to be matched. Okay, why? Because you can clearly see since there are only two non-dimensional numbers, so it basically tells us that the viscous stresses as well as the pressure gradient force, this pressure gradients are the driving factors in the case of a flow field, in the case of this current flow field, and thus these two driving factors should indeed match each other, so that the equation is satisfied, right? So these two terms should match each other, so that the the dimensionality of the equation is satisfied, because we are not telling that any of these two terms are insignificant. We are saying that both of these terms are significant in the governing equation. So it ideally means that the scaling or the order of magnitude of this value, this non-dimensional number and this non-dimensional number should match, because ideally this is the order of magnitude of these terms are unity, right? This is 1, this is 1. So this is the coefficient that is being used to non-dimensionalize these flow variables, right? So it tells us that since both of these terms are significant in the governing equation, then these two non-dimensional numbers should match each other in the case of a model and a prototype. Okay, so that's what the first approach that is being used, right? Using governing equations to obtain the non-dimensional numbers. It is the first approach that is being used. So I'm sorry, I'll just wait for 1 minute. So I hope you understand. Just wait for 1 minute, okay? So, sorry for the delay and thanks for waiting. So, here we again, this is an example taken by Professor Gupta in the lecture. So, if you have any doubt here, you can ask. But if I am unfortunately I'm not able to clear your doubt, you can always go back to the lectures and see the lectures again, so that the doubt is properly cleared. And obviously from my side, I will try to clear the existing doubts in the next session, as well as you can, if you have any persistent doubts, you can ask those doubts in the discussion forum as well. Okay, so I hope it is clear. So this is an example of cavitation in torpedo. I guess it was well discussed why cavitation occurs, so I won't dive deep into that, but still let's look into the question. A torpedo having a diameter of 20 centimeter is seen to be on the verge of cavitation at the speed of 30 meters per second when running 10 meters below the ocean surface. Okay, so 10 meters below the ocean surface. Velocity is 30 meters per second, and it is on the verge of cavitation. So at what depth must it run if it is to travel at 50 meters per second? So in this case, you will see that there is no concept of a prototype or a model. So here they are basically dealing with the same model or prototype. They are not dealing with different land scales, but actually dealing with different values of the flow parameters, just so as to know that how tweaking or how modifying one flow parameter would require the proportionate change in the other flow parameter, so that this non-dimensional constant, this non-dimensional number, that is the Euler's number or the Reynolds number, remains constant for both these two instances. Okay, so this is what been ideally done in this example. So it is told that the torpedo is in the verge of cavitation while running running at the speed of 30 meters per second at a depth of 10 meters. So given that the torpedo would remain in the verge of cavitation, so given that the torpedo would remain in the verge of cavitation and would have the same diameter, but it has to travel at 50 meters per second, right? So the parameter that they are changing is actually the velocity, but the the thing that is kept, the things that are kept constant are the torpedo diameter and the fact that the torpedo would remain in the verge of cavitation, right? This is also important. So this is not changed in both the instances. So they are asking that if the torpedo has to remain on the verge of cavitation and is of the same dimension, then at what depth should the torpedo travel so that it has a speed of 50 meters per second? Okay. So what should be the depth so that the flow physics remains the same for these two trials or two runs of the torpedo? Okay. So here fluid number does not need to be matched because we are dealing with piezometric pressure. Ideally this known as a piezometric pressure. So instead of dealing with gauge pressure only, we are dealing with piezometric pressure. So that's what this representation ideally means. But again, this is very important. Okay, this next line is very important. But since cavitation is involved, the Euler number is now to be matched. Okay, here as I have discussed in the previous derivations, that since now till now we only know that if we modify the equations, like if we incorporate the gravitational term in the pressure gradient term, we can ideally deal with two non-dimensional numbers that need to be constant for both the cases, right? That need to be matched. So, but it may happen that while matching the two non-dimensional numbers, that is at least what we know this far, that we would have Reynolds number for a particular fluid flow problem. We will have Reynolds number and Euler's number. Okay, and we would have incorporated Froude's number in Euler's number. So that's simple. But okay, that's not actually what conceptually means. It basically means that the effect of Froude number is being incorporated in the pressure gradient term that is being dealt in the while non-dimensionalizing, and that is incorporated in the Euler's number. So that's what actually it means. But let me just say that we are dealing with Reynolds number and Euler number, and these are two non-dimensional numbers that has to be matched to get a better idea of how the different flow parameters would change if we change other flow parameters in the fluid flow problem. Okay, so but now the thing is that it may happen that while comparing these two non-dimensional numbers, you may end up with different values of the flow variables. For example, what I mean to say is that if you compare the Reynolds number instead of the Euler's number, and for this case you may end up with a different height. Okay, now again, if you are dealing with Euler's number, then you may end up with a different depth. I'm sorry, height, I said depth. Okay, so these two may result in different values of h or depth. So it is up to you as a researcher to decide which depth is correct, or which is the value that is actually correct. Actually correct in a sense is that is more aligned to the actual physical problem. So here you can see that it is cavitation that is actually the driving factor of design, because once the torpedo goes under suffers cavitation, it becomes like it is quite detrimental for it. So the design factor or design criteria for this torpedo is the cavitation, right? The cavitation pressure. So we want to avoid that. So that's why this is more important rather than us having to compare the Reynolds inertial forces and the viscous stresses in the case of Reynolds number. So comparing the cavitation pressure, because we cannot let the pressure go beyond the cavitation pressure. Like if it goes beyond the cavitation pressure in the case of the second run, then it is no good, right? It does not satisfy the basic design criteria that has been used to design the torpedo, right? So it is more important. That is what I basically mean to say. The cavitation factor is more important. So ideally, as a researcher or engineer, we compare the Euler's number in the case of such problems, in case of torpedo or any other problem where cavitation pressure is the design factor that is being used to design or create the particular system, right? So that's why it is very important to know what's actually driving the design of the particular system. Okay. So given we know that, we now compare the Euler's number. So it is basically rho v naught square by p naught minus pv, that is the cavitation pressure, that will be equal to rho, for a prototype, that will be equal to rho v naught square p naught minus pv for the model. And in this case there is no no difference between the prototype and the model. It's basically two different runs of the same model or the prototype by having different flow parameters for different runs. Okay, so that is what being actually done here. So now we evaluate because we know v naught for both the cases. Rho is constant because we are running it on the same seawater. So we evaluate this p naught minus pv factor, where p naught we take it as, let me just see that p naught can be taken as p plus rho z minus p naught reference minus p plus rho z minus p naught cavitation. And here we take the assumption that we take the datum as the ocean surface, where p is equal to p naught and z equal to 0. Okay, so here p will be equal to p naught, so this will cancel and z equal to 0. So this term will be 0. So we will be having only this term, right? So it is basically here. So we have p naught minus pv will be equal to p naught minus pv minus rho gz. So given that we know the values of, we substitute the value on this. So we substitute the value of pv. P naught is basically atmospheric pressure. So let me just mention it. So pv is 2.3 kilopascal. So we substitute the values here and we see that p naught minus pv for the model is equal to 200 kilopascal, right, at this particular depth, for depth of 10 meter. So we just need to vary, in the case of the model we need to vary the velocity, because that is what actually changing, and we need to find the corresponding height. So that's what we actually do. We compare the Euler's number. Since rho will remain constant, we need to since rho will remain constant, so we get p naught minus p for the prototype will be equal to p naught minus p model. Like we can interchange any of them, that's completely fine. But you need to check that if you are considering for this, then you need to take the other one as a prototype. Okay, so that's what important. So we do that. We deal with modify the equation. You can see that it will be 200 kilopascal by the into the square of the velocity of the prototype and the model, right? So we know it is 50 because this is what we have changed. So 50 by 30 whole square. So once we evaluate it, we get that p naught minus pv equal to 555 7.7 kilopascal. So again we just substitute the same formula that we have used for the evaluation of p naught minus pv in the case of the model that we choose. So substitute that. Substitute z as h, this is required. So this we know, this is known, rho is known, g is known, so the only unknown is z, that can be easily found. So we find that z or h is equal to 45.2 meter. Okay. Similar to that, we have the power requirement in the case of a blimp. So let me just, this again dealt in the case, dealt in the lectures, but let me just see. Okay. To estimate the power required of a blimp for traveling at 10 meters per second in air, it is proposed to test a 1/20th scale model. Now here you see the concept of model comes to the picture of it in water. Okay, then this part I have not solved. This is dealt in the lecture. So let me just. So what should be the velocity of the model in the water, and what will be the prediction rule? What will be the prediction rule for power required? So this part I have not discussed. But you can see in the lectures, but we will see how we find the velocity of the model if the fluid is changed to water and the model is actually a scaled down version of the actual prototype. Okay, here you can see the scaling down is actually done, or the real concept of the prototype and the model comes in the picture, right? So that's why this question is important. You get an idea of how different, how the concept of prototype and the model comes in the picture, and how it is actually useful. And you can again see that to test this scaled down version, you have also changed the fluid itself. Initially, your prototype runs in water, so in air. I'm sorry, but now you're testing your model in water. So you can see that you'll eventually see when you read more that there are various instances where the actual prototype, if it travels in air, so the tests of or experiments of those prototypes are very easily done in the case of water, right? They are in the case are done in case of in water, right? Those experiments where the prototype actually travels in air, but the experiments of those prototypes on a scaled down model are actually done in water. So there are various advantages of doing such experiments in water. One being that the density of the water essentially remains constant for throughout the experiment. It's very important. What to say? That's a very important fact, or a very important result that is useful for conducting experiments in water. But moreover, you will see that while it's just a mathematical conclusion that while comparing non-dimensional numbers, that if we would have kept the fluid same, we will see that there will be a certain jump in the values of other parameters, because the density, since it remains constant, and since there is a huge discrepancy in the dimension of the prototype and the model. So, and this discrepancy actually this discrepancy is actually seen as a result in the increase or decrease of the dimension of the increase or decrease in the dimension of the prototype or the model, or an increase and decrease in the magnitude or the velocity required to conduct the same experiment in the same fluid. Okay, so this discrepancy is being handled by using a different fluid of different density, ideally water, that helps in conducting experiments that has high discrepancy in the length scales, and this discrepancy in the length scale that would have eventually resulted in discrepancy in the velocity scales. So this discrepancy in the velocity scale is smeared out or cancelled out by using a high density fluid, that is in this case is water. Okay, so I hope it is clear, and this is actually very that comes by dealing different kinds of problems, and this is one of the things that I have read in I myself read in a fluid mechanics book by Sengel, so you can refer to that. Okay. Okay, so here we see that similarity for flow in immersed fluids requires matching of just the Reynolds number, since there is no free surface or cavitation in this flow. Okay, so as you see in the previous problem, you saw that how the matching of the Euler's number was the primary concern for, or was a primary factor for deducing or for deriving the required flow parameters. Similar to that, in the case of flow past immersed bodies or flow past submerged bodies, it is told that matching a Reynolds number is enough, or is actually ideal for getting the unknown parameters, right? And since there is no cavitation, Reynolds number can be matched. Okay, and would give good results, and say experiments show that this matching of Reynolds number would give very good results, and that's why the author suggests that uh, matching of Reynolds number can be done in the case of flow pass immersed bodies where there is no cavitation. Okay? So since there is no cavitation, we match the Reynolds number and we see that rho v naught L naught mu for the model should be rho v naught mu naught rho v naught L naught by mu for the prototype. And since the fluids are different in this case, we need to deal with different rho p by rho m and mu p by rho m. So we need to know these values since the fluid is different. In the previous case, the fluids were the same, so essentially these two terms would have been constant for the previous experiment, but since this is different in this case, so we need to know how these are different for air and water. So once we know that, just substitute the value here. Since we need the velocity of the model that is being tested in water, we deal with this, we modify the equation and get this final form. Substitute the value of the density of water and air as well as the length scales and viscosities to finally get then the velocity of the model in the water should be 15 meter per second. So here you can easily see that if the fluid was same, right? If the fluid was same, this would have been actually then the density would have remained the same. So it would have been say density would have remained the same. So this would be cancelled out, this would be cancelled out. But you clearly see, since the length scale has a changes by the order of 20, so the velocity scale will also change by the order of 200, right? Since these two will multiply with each other, since these two terms will multiply with each other, we'll see that the velocity of the model should actually should be 200 meter per second. It's actually a very difficult thing to achieve in the case of very highly advanced wind tunnels as well. So reaching 200 meter per second is very difficult. So that's why to handle that discrepancies, the researchers find it ideal to change the fluid for the experiment so that this discrepancy in the velocities can be handled. Okay. So this is one of the approaches that we discussed. So there are two more approaches that we'll discuss today. So second is a scale factor approach. Okay. So previously we have seen that till now that just from the governing equations and knowing the scales, like we have just assumed that all the scales in the flow field would vary as L. Say that we assume that all the scales of the flow field will vary as L, and also assume that the velocity scales would remain the same along all the directions. Because it is because of that only we were able to, let me just go back to the equation. It is because of that assumption only we were able to non-dimensionalize this vector from the equation by the same velocity component and the same length scale. Okay, here, which is ideally not the case in different fluid flow problems. Okay, in the case of boundary layer, this is not at all valid because different governing equations along the different directions will have different length scales that will govern the flow field, right? So you can clearly see this method of matching the non-dimensional numbers in the case of the prototype and the model is not ideal. I'm not saying it is not good. It is good and it is quite accurate to some extent and gives us a good, gives a very good idea of how the parameters changes, but it's not always accurate. It's quite limited, right? So in order to deal with this discrepancy or deal with this issue, the concept of scale factor approach came into picture. So here it basically tells that what we have previously discussed, the similarity in the geometry, similarity in the motion, I'm sorry. So as I was saying, similarity in the motion and similarity in the forces. These three conditions should be satisfied. So it basically implies there should be geometrical similarity, there should be kinematic similarity, and finally there should be dynamic similarity, so that we can essentially say that the flow physics is same for both the prototype and the model. Okay. And this approach is far more general and powerful than we discussed previously, because in that case we are just dealing with, ideally we are just dealing with three non-dimensional numbers that we got from non-dimensional in the equation, assuming that the length scales and the velocity scales would remain same for all the three independent coordinate directions, right? Okay. So we see here that the geometric similarity requires the ratios of all corresponding dimensions in the prototype and the model are equal. Okay, so it basically means that, say if we are dealing with a, say, pipe flow or flow or cylinder, then the radius of the prototype and the radius of the model should scale by a same factor. They should scale by a constant factor. Okay, they may not be same, but at least they should be congruent. They may not be exactly equal, but they should be similar. And similarity comes by the concept that this the length scales of this the prototype and the model should vary by a constant factor. Okay. That's what is mentioned here. So as I mentioned, this complete similarity implies that the scale holds for each of the other quantifiable quantities, such as velocity, time, stress, and power. So this would, as I said, this would gradually come into sense, like how the geometric dynamic similarity and the kinetic similarity are in turn heavily dependent on the geometric similarity of the prototype and the model. So we gradually see that. Okay. Similarly, in the case of velocities, the magnitudes as well as the direction of the flow velocities at homologous points must remain the same. Homologous points, I guess, is discussed in the lecture, so I won't again go back. It basically means identical points. Not identical points, what to say? Similar points in the correspondingly similar dimensions in the case of a prototype and a model. I guess it's the most simplest way to explain it, but if you have any doubt, I again suggest that please go back into the lecture so that you can get a proper idea. Okay. So it basically means that a geometrically similar prototype and a model are said to have kinematic similarity if all the kinematic quantities such as frequencies, RPM, rounds per minute, is basically rotations per minute, angular velocity omega, acceleration a and the angular acceleration a, or the volumetric flow rate q and other kinematic quantities have a constant scale factor. Basically means that they can vary as different scales. These parameters, these kinetic parameters, that is frequencies, RPM, angular velocities, these would scale. This should scale. The ratio of the frequencies, RPM, angular velocities, and angular acceleration, volumetric flow rate between the prototype and the model should scale as should have a constant value of the scaling factor, but as well as it is important that this scaling factor should remain same for all these cases. Then only we can say that the prototype and the model has achieved kinematic similarity. Okay, and that can only be achieved if the prototype and the model has achieved a geometric similarity. Okay, that's why it's important. Okay, so we consider an example for implementing the concept of scale factors in the case of a volume flow rate. Okay, so volume flow rate, we know that volume flow rate can be written as Q is equal to area and the velocity. Okay, rho is assumed to be constant. If it's assumed to be constant, then it is volume flow rate other than a mass flow rate that becomes a very important flow parameter in the case of the particular future problem. Okay, so we have the volume flow rate as A into V. So say that our volume flow rate will scale as a the volume flow rate between the prototype and the model scales has a constant scaling factor of kq. Okay, basically means that qp by qm, so it is equal to k dot q. Okay, similarly to that, for area, since it is the dimension of area would be length into length square, so it should have the scaling factor should be multiplication of both those length scale, so it is kl square, and velocity should be kb, right? So it essentially tells us that this volume flow rate, since a multiplication of a into v, then these scaling factors should be equal. That is what being told here, right? Should have constant scale factors, right? If all the if all the kinematic quantities such as have constant scale factors, so this should be constant, right? It's not a variable. So we can ideally say that if q varies as k dot q, then it should be equal to the scaling factor of the area multiplied by the scaling factor of the velocity, right? Because the very mathematical expression of volume flow rate is given by q into av. Thus, the scaling factors should as well satisfy the governing equation that is designed to express the volume flow rate. Yes, volume flow rate essentially it means that only. So scaling, if q is equal to av, it means that the scaling factor of the volume flow rate should be equal to the scaling factor of the length scale square into the scaling factor of the velocity scale, scaling factor of the velocity. So essentially that what we have written here is kq should be equal to kl square kv. So if we now compare the volume flow rate between the volume flow rate between the prototype and the model, so it will essentially have that. This is what I have written here. qp would be equal to qm. So again, since qp would be lp square into vp, then qm would be lm square into vm, right? And since lp by lm is what? kp square, so kl square, kl square is equal to kv, then it will be equal to k. That is what exactly what we have got. So now we say that since these are equal, then the ratio of these scaling factors k dot q, kl square, kv should be equal to 1. Basically it means that these scaling factors should form a non-dimensional number, right? That's what we are essentially trying to say, and that's basically the very concept of scaling factors, right? So once we know the physical parameter that we want to compare between the prototype and the model, then once we know the scaling factors of this physical parameter, since that is being known here in the case of volume flow rate, so the ratios of this these scaling factors should create a non-dimensional pi number or non-dimensional number that can be used as a non-dimensional parameter to characterize the flow field, right? To characterize the flow experiment or flow field, whatever we want to characterize, right? So it essentially tells us that this should be a pi number. This should be a non-dimensional number. It is quite obvious if you just compare the units of this case, but it is told that this should be a non-dimensional pi number. So here we see that that's what being compared in the case of, this is what being exactly compared in the case of a in this equation. I'm sorry, and you will see that you will eventually see that if you are in the later part of the course, we will be eventually dealing with pumps, turbines. So you will see that this parameter is actually one of the very fundamental part, or integral part for understanding the functioning or characterizing the pumps and the turbines. Okay, if I am not wrong, I may be wrong, but you'll see that if I'm not wrong, this will come into picture while we are dealing with understanding with pumps and turbines. Okay, in turbo machinery. So, okay. So similar to that, again we see that the prototype and the for dynamic similarity, we see that the prototype and the scale model are said to have dynamic similarity if the net forces at the homologous points in the two are related by a constant scale factor Kf. Okay. However, the force at a point in the system is related to the kinematic quantities as well. That's what I wanted to say. A system cannot achieve dynamic similarity unless and until it has achieved kinematic as well as geometric similarity. Okay. Similar to that, we see that F is equal to ma, it's basic Newton's second law. So if we say F scales as kf, mass scales as km, and acceleration scales as k, obviously between the prototype and the model. So again, the ratio of these scales, like since these two are equal, if we take this as a denominator, this should again be a non-dimensional number, right? So this should again give a non-dimensional number. So okay, here I guess it just here they have just dissociated how km can again be represented in terms of the other kinematic and geometric quantities, kinematic and geometric scale factors. So it is basically if the density scales as rho and length scales as L, represented km as k rho into kl cube. Similarly, they represent k as kv square by k, velocity square by length scale factor of the length. Okay, so I've done a derivation here. You can just look in the notes. So I'm just going to go deep again. Okay, so this is again very important. Similarity requires that not only the total forces on the prototype and the model, and the total forces on the prototype and the model elements be scaled by unique factor, but the same factor must scale every component of force that make up the total force vector array. So you can say that if the force, if you are trying to compare the force at a particular point in the prototype and the model, and if this force at a particular point is actually resultant of various forces that acts on different points on the flow field, say, then these different components of the forces should also vary by the same scaling factor by which the resultant force between the prototype and the model varies. Okay, so that's very important. And obviously, since force is vector quantity, the direction of each component of force must be the same, right? And the magnitude must be scaled by the same scale factor k. So now we compare in the case of, now we'll just see an example, the scale for the viscous forces. Okay, then we know that viscosity is usually what to say, comes into picture, comes into manifestation in the case of fluid flow problems, or manifests itself as the shear stresses that acts on the fluid. Right? So we say the shear force would be equal to shear stress into area, because force is equal to stress into area. So say for Newtonian fluid, we have shear stress that to scale as k tau is equal to k mu kv by kl. Okay, and area is kl square. We simplify the terms so that we cancel out the required scales. Then we have then just if you multiply these two, you get the kf mu, this k shear forces, scale for the shear forces would scale as k mu kv kl. Okay, the product of k mu kv and kl. Okay, where k mu is the scale of the viscosity. So a non-dimensional number, a non-dimensional pi number from this would be actually f mu by mu vl. Okay, so this is a non-dimensional pi number from this approach, like we get this as a non-dimensional pi number. Okay, then what we can do is, now once we know how the different types of forces. It's basically the shear forces, the pressure force, the body force that scales in the flow field. Then once, as I told in the previous example, like once we know which among these two forces would actually balance each other, or would actually be the driving forces of the flow field, then since both of these two forces are considerable, or both of these two forces are considerable in the case of this particular fluid flow, then actually these two forces, these two forces, basically these two forces must balance each other, right? And in the case of once we non-dimensionalize the equations, the two non-dimensional numbers that acts as the coefficient in front of the non-dimensional forcing terms, then these two non-dimensional numbers should balance each other. That's what actually I discussed in the previous section or previous approach. So in this case, they're basically saying is that if we know how the forces scales, and if we know that these two forces, say the inertia force or the viscous force, say the inertia or the pressure force, balance each other, then what we can ideally do is that we can ideally just equate those scaling factors that we have got after implementing the required scale factors to the flow variable, to the different flow variables in the case of a particular forcing term. Like say in the case of the shear force, we scale the, by implementing the particular scales to the flow variables, we get a non-dimensional pi number. Similar to that, if we are dealing with inertia force, we will be able, by applying particular scaling factors, we will be able to achieve a non-dimensional pi number. Then if we know that the inertia force and the viscous force balance each other, right, then we can say that then we can say that, then from that we get a very interesting result. Okay, so we say that we equate the scale factors of various component of forces to obtain modeling rules, right? That's the interesting result. After we compare the scale factors for different components of forces, or basically the various driving forces in the flow field, we get the modeling rules, basically similar to the previous case that we have discussed. Like in previous case, it is from the governing its equation itself that we get that it is a Reynolds number that we need to compare. It is a Euler's number that we need to compare. But here, just by having the idea of the scales of how the different forcing terms may vary. Okay, so yeah, the two approaches might similar in itself. That all the three approaches are similar in one way or another, but there is certain slight difference or silver lining between these different approaches that makes these three approaches different from each other, and makes them quite elegant in their own way. Okay, so I must say this approach is a bit more general than the previous case, because in previous case we are only dealing with three non-dimensional numbers, that is Euler's number and the Reynolds number, and if we incorporate the body force term in the pressure gradient term, then we are only essentially dealing with two numbers. So it reduces the scope of the problem that we can deal with. But in this case, if we know what are the driving forces or the factors that will drive the flow, that may be quite different depending on different fluid flow problem, right? Because it may happen that now we know that the body force term, instead of being a gravitational force, is actually electromagnetic force. Now we know that we do not need to go back to the governing equation. If we know the scaling factors of those body force terms in the case of the electric potential or the electrostatic force that acts as a body force, if we know the scales, if we properly know the scales of these body force terms, and we know that this electrical what to say, let me just write it, that electromagnetic force, if it balances the viscous forces, and if we know the scales, then we can just essentially equate these two non-dimensional pi numbers that we get after rearranging the scaling factors, Then after equating that, we will finally get the modeling rule that is required for that particular model or particular system, right? Modeling rule. So this is the elegance of this different approach, this scale factor approach. Okay, so that's what I wanted to mention. So similar to the, now if we have if we compare inertia force and the stress what to say viscous forces in the case of a particular free flow problem, then we will eventually see that if these are the two forces that are dominant in the case of a particular free flow problem, then a modeling rule that we get is actually very beautiful result. It's actually the Reynolds number only. It's only Reynolds number that is comes into picture, that it what to say, essentially tells us, like, if we know the driving forces in the flow, the only non-natural number that we need to compare is the Reynolds number. That's the final conclusion. Okay. Similar to that, various problems will have different modeling rules that we need to find out by imposing, by understanding the actual driving forces, and then finding the modeling rule, which will indeed give you a non-dimensional number, which will ideally be a well-known non-dimensional number. So this is the approach that we usually follow. And after that, just compare these two non-dimensional numbers in the case of prototype and a model, and then get the required value of the parameter that you need to find in the case of model or the prototype. Okay. So there is an example in the lecture, so I'll just briefly go through it, because I have one more topic to discuss. It is the Buckingham's pi theorem. That's very important again. Okay. A seaplane is being designed for a takeoff speed of 100 km/h. Okay. Model tests are to be made on a 1/10 scale model. At what speed should the model be towed to simulate the takeoff condition? Okay. Okay. Let's just consider the first part. Okay. Then we can just discuss the second part from the notes, or you can just look at the lectures again. Okay. So similar to the problems that we dealt previously, here we are again dealing with a prototype and a model. So it is told that since the only thing that is being changing is the length scale, and we are asked that if there is a 1/10 change in the length scale, then what should be the corresponding change in the velocity, so that we could simulate similar conditions that may exist while the plane takes off. Okay. So you can see here that since the problem tells us that since it is taking off and it has to move against the gravitational forces, then it's actually the balance between the inertia and the gravitational force that would ideally give us the right modeling rule. Okay. So if we equate the inertia force and the gravitational forces with the respective scale factors, we will see that we'll end up with this modeling rule, which will see that it's essentially a square of the Fruit's number. Okay. And now since we know that since gm and gp will remain constant, it basically the acceleration due to gravity, it will remain constant, at least for this case, since the plane does not take off very high a very high distance from the center of the earth. So gp and gm will essentially remain constant. And also you will see that since we know the velocity of the prototype, we know length scales are given, so we just need to compare the equate these terms, and then we finally get that velocity of the model is equal to 31.6 km/h. Okay. So next one is also similar. I won't deal with since we are short of time. So now there is a third approach. Okay, and that is known as the Buckingham's pi theorem. Okay, that's again as I mentioned, it's a very elegant way to get a very good idea or very good understanding of what would actually be the non-dimensional numbers that would govern the flow field. Okay, but because till now we were just doing, like, essentially we were just assuming some certain we are what to say, depending on our assumptions a lot, like assumptions or the idea of the fluid mechanics problem a lot, because since we know that we inherently know that in a pipe flow the pressure forces, pressure gradient term would be significant, right? It will be dominant. So we know that will drive the flow. In the case of flow over flat plate, it is the inertia force that will drive the flow. So there are various well-known flow established fluid flow problems. From that we can tell that this would be the driving factor. So these are the terms that we need to equate to find the non-dimensional number or the modeling rule. But the case becomes complicated when we are dealing with such problems. So different kinds of problems or different kinds of systems where we do not inherently know what would actually drive the flow. So if we do not know that, then there is no point of implementing the scale factor law, right? Scale factor approach, because we do not know that what are the forces that will actually govern or drive the flow. So one way to tackle that issue is the Buckingham pi theorem. That again will hand us with different non-dimensional numbers, but at least it will give at least a crude idea that that these are the numbers, these are non-dimensional numbers that exist. So you need to deal with these non-dimensional numbers, and after dealing with that, after doing the experiment or tweaking these non-dimensional parameters, you will know which is a parameter that's actually affecting the most, that is actually driving the flow, and which the non-dimensional parameter that is affecting the least, which essentially can be neglected because it's not having an integral role in defining the flow field. Okay, so given that idea, so the Buckingham pi theorem states that if there are m physical parameters in a particular fluid flow problem, and there are n fundamental parameters in the case in that particular fluid flow problem, then there should be m minus n non-dimensional parameters on pi terms that would govern the flow field. Okay, so the fundamental parameters usually in the case of a fluid flow problem, if there's no heating or no additional electrical input that would essentially drive the flow, like if for simple fluid flow problems, usually the fundamental parameters are the length scale, the mass, and the time. These are the three fundamental parameters. Usually these are the three fundamental parameters. Okay, so depending on the problem, you need to find out the fundamental parameters as well as the physical parameters. Okay, so we will take a small problem so that you can get an idea of the implementation of the Buckingham pi theorem. Okay, so in the question it is told that the particular fluid flow problem depends on the, let me zoom it a bit. It is told that the particular fluid flow problem depends on the diameter of the system, the volume flow rate, the rotational speed. Say rotational speed of the, say if you are dealing with pump, then you can say that the rotational speed of the pump, then G into H, it's again one parameter as it's mentioned here, rho, mu and P. These are the these are the parameters upon which the our current problem depends upon. Okay, so from that from this we get an idea that since there are 1, 2, 3, 4, 5, 6, 7 fluid flow parameters, and in that problem, because we are only dealing with simple fluid flow problem without any heating or electromagnetic force application, at least within the control volume, so the fundamental dimensions would be mass, length and time. Okay, so number of fundamental dimensions is 3, so we will have 4 pi terms. Okay, then there's again a concept of repeating variables. So I guess there are certain rules and regulations for choosing the repeating variables. So I guess for that you should ideally look in your lectures or any standard fluid mechanics book of what should be repeating parameters that you should choose for determining the these non-dimensional numbers. Okay, and one of those as far as I remember, one of those rules for choosing repeating variables is that these three variables, okay, these three variables should not themselves constitute a non-dimensional number themselves, okay, like by certain product or division, these three variables should not constitute a non-dimensional number among themselves, okay. So this is one of the rules. So keeping that in mind, say for a particular problem we have taken d, n and rho as the repeating variables, okay. So from that, if you want to evaluate the d, n and rho, okay, so repeating variable basically means that repeating variables would be equal to the number of fundamental dimensions, okay. So it essentially tells us that, see, if d, n and rho are the repeating d, n and rho are the repeating variables, these terms would actually be incorporated with the remaining terms, that is q, gh and mu. This would be incorporated with these three d, gh, mu and ps. These four remaining flow parameters, this will incorporate themselves with these four remaining flow parameters and then form a non-dimensional number, okay. So this is the concept of repeating variables. So let's just take this example so that you get your concept quite clear, okay. So if we want to find the first non-dimensional parameter, so the first parameter that we deal with is q, okay. So we'll tell that pi 1 would be equal to q into rho to the power a, n to the power b and d to the power c, okay. Because these are repeating variables, so we say that this would vary as the powers of a, b and c. Then we dissociate these terms in their fundamental dimensions, okay, in terms of their fundamental dimensions. Then q is volume flow rate, which is equal to L cube into T minus 1. Similarly, rho would be again mass by volume, so m into L to the power minus 3a. Then n is rotations per minute, then it would have a dimension of 1 by t, so it is T inverse to the power b. Similarly, d would have a dimension of length, so we can take L to the power c. And here again, this side, this pi, since it is non-dimensional, it would have a dimension of 1, okay, it will be unity. So for the first term, we take all the powers common for L. So we have L to the power 3 minus 3a plus c, okay, we write that. Then we have t, similarly for t we have minus 1 minus b, that's all. Then from m we have only a, and since this product should give the value to be 1 in the left hand side, so all these terms should have their their dimension as unity, okay. That will only be possible if their powers is equal to 0, okay. So it essentially tells us that a would be equal to 0. From that we can from here we can say that b would be equal to minus 1. If we equate minus 1 minus b equal to 0, then we get b equal to minus 1. From that we substitute the value of a here to get c equal to minus 3. So we get that the first non-dimensional number that we will dealing with would be equal to q by n d cube, okay. So it was L square. Let me just go back to the previous slide if I'm not wrong. Sorry, quite going up and down in the slides. I just need to check. Okay. So you can just see here itself. Okay, that's the beauty what I was discussing about. So here, if you see L square v, the dimension of L square v would be L cube by time, right? So similar to this, we have that in this problem, in the case of a flow in a pump, the first non-dimensional parameter is equal to q by nd cube. The dimension of this would be again L cube by t, right? So as I told you, this number itself again plays a very important role in the design of pumps. We will eventually see that. So following similar steps, we get pi 2 would be equal to gh into rho a and b dc. We again dissociate g into its fundamental dimensions. for similarly for the repeating variables. From that we get that pi 2 is equal to gh by n square d square. This again a non-dimensional number or pi number. Again for pi 3 we get that mu would be equal to p rho a n b d c. So where mu 3 is equal to mu in a dimension of ml minus 1 t minus 1. Then again dissociate the repeating variables in terms of the fundamental in terms of the fundamental variables. So we get that pi 3 is equal to mu by rho n d square. So I guess I forgot to do for p, but here now you get an idea how to implement the Buckingham pi theorem. Okay, so I guess we are well beyond of our time. So I hope I was able to make you understand the difference between the three approaches, how they are different from each other, and how they are quite elegant in their own way. Okay, for simpler problems, the first approach, the governing equation problem, is quite elegant. It's very simple. We deal with only two non-dimensional numbers and then find the relationship between the parameters for the prototype and the model. Similarly, for the second approach, for the scale factor approach, it's again a more generalized version of the previous approach, where having an idea of the driving forces can help us to determine the scaling rule or the modeling rule that can help us to get the non-dimensional number that we need to deal with for getting the the value of the parameters in the case of the prototype or the model. Then finally we deal with Buckingham pi theorem. This again a very much more generalized approach, where without even having an idea of what are the governing forces or driving forces that drives the flow or governs the flow, without even having that idea, we can at least deduce the non-dimensional numbers or parameters that can help us to know how can help us to get the non-dimensional parameters that govern the flow field. And by having an idea of the non-dimensional parameters, these non-dimensional pi numbers, we can play with these non-dimensional pi numbers if we are conducting experiment, obviously, and then see which parameter actually affects the flow most, and which variation of which parameter affects the flow the least, and we can know that which parameter actually drives the flow. Okay, so I hope it was clear. So if you have any doubt in the approach for the Buckingham's pi theorem or the scaling approach or dimension analysis, please put your doubt in the discussion forum. Or again I say, we have a teaching session again on Monday. Please attend that also. And if you have any doubt, again I suggest please go to the lectures of Professor Gupta, so you can get your doubts quite clear by looking at the lectures. Okay, so I hope it was a very nice session. So thank you and good night.